Come here. Here, I need some help.
Put that there for you. Good. Where's that from? Yeah, there. That'd be okay. Move it along there. It'd be okay, it's only. Do you want to move it along?
Good evening, YouTube. Welcome from Horizon Community College for Physics Paper 1 live revision the night before your next exam. Starting us off this evening, we have Hughesy, Miss Hughes, who is going to be introducing energy stores and transfers. So pay attention, guys.
Right, so good evening. So we are going to start off with Spec 1. So we're going to start first of all, by we're going to do a mind map on energy stores and transfers. So first thing we're going to do is we are going to look at all of the energy stores. So we're going to make a big list of them. So we have electrostatic, we have chemical, kinetic, gravitational, magnetic, thermal, and nuclear. Okay, so they are all energy stores. Okay, so what they could do in your exam is they could ask you how an energy transfer takes place. So it's really important that you know the energy stores and you can then put them into an energy transfer. So if we look at one example of an energy transfer, we'll look at a ball falling to the ground. Okay, so we'll look at what the initial energy is to start with. So initially, when the ball is held up high, it has gravitational potential energy. So I'll shorten that down to GPE. Now, when the ball is released and it falls down to the ground, that gravitational potential energy is transferred into kinetic. So as it falls down, kinetic energy is released. When the ball hits the ground, it's then transferred into elastic energy. And a little bit of heat is also given off. So, heat in this case is wasted energy, basically. Okay, so in an energy transfer, the wasted energy is transferred to the surroundings. Can't fit it all on. And what that causes is it causes the surrounding air to heat up. Linking into that, if we also look at the conservation of energy. Okay, so this wasted energy links into conservation of energy. So the definition is energy cannot be created or destroyed only transferred from one form to another. Okay, so that is conservation of energy. Okay, so also in this topic of energy is the equations. Sorry, we're just having some behind the scenes difficulties. So obviously you all know for your exam that you do need to learn some of the equations. So they might get given to you, they might not. Okay, so we're going to make a list of the ones that you need to learn. I'm going to short them down because I can't fit them all on this paper. So the first one is the equation for power. So power is the energy transferred divided by the time. If you want to put that into a triangle, energy on top, and then power and time at the bottom. The next equation we're going to do is kinetic energy, so I'm going to shorten it down to KE. So the equation for kinetic energy is a half, so 0.5 times the mass. See if I can fit this on. Times the speed squared. We've got elastic potential energy. So for this one we've got 0.5 times the spring constant times the extension squared. And the last one I'll try and fit on down here, gravitational potential energy. This one's quite an easy one to remember. Mass times gravity, I might be able to fit it on, times height. Okay, so they're the equations that you need to learn, because they might not be given to you in the question for your exam. Now I'm going to, in fact I'll do it on a different piece of paper. While we're looking at equations, we'll look at what the units are for each one of these. So, put this here. Right, so the units, it's really important that you learn the units for your equations because you do get asked to put them on the end of your answers sometimes. So the units for energy can also sometimes be referred to as work done. So be really careful in the question. This is measured in joules, so represented with a J. Mass is kilograms. Speed is meters per second. Extension is measured in meters. Height is also measured in meters. And then spring constant measured in Newton meters. Okay, so they're units for all the equations that we have just gone through. So what we're going to do now is I'm going to show you one practice question linked into energy and energy transfers. Okay, so it's using those equations. In this question, they've been quite nice to you because they've actually given you the equations. Okay, so this is the question that we've got. Okay, so the diagram shows below a girl skateboarding on a semicircular ramp, and then below you've got all the information about the question. Okay, so first of all, we're not going to ignore the diagram because here is a really important number. So it says 4 meters. The girl has a mass of 50 kilograms. It says calculate the gravitational potential energy of the girl at the top of the ramp. Use the equation below. So they're giving you the equation, and they've also given you the gravitational field strength or gravity. So all you have to do for this question is simply put the numbers into the equation. So the mass is given to you in the question. So we've got 50. We're going to times it by the gravitational field strength, which they've given you also in the question. Always use the number that they give you. Times by the height. The height is up here in the diagram. So times by 4. Obviously put all that in your calculator, just timesing it together, and the answer you should get is 1,960. Always check that the units are on the end of your answer, because if they're not given here, you would have to put joules on the end of your answer. That could be worth a mark, so make sure you check that it's there, and if it's not, make sure that you write the units down. Okay, so another question is calculating the kinetic energy. So again, get the highlighter out and highlight the numbers in the question. So a girl has a speed of 7 meters per second at the bottom of the ramp. Calculate the kinetic energy of the girl at the bottom of the ramp, and again it's giving you the equation to use. So 0.5 times the mass. Well, the mass was further up in the question, so the mass is 50, so 0.5 times 50 times by the speed squared. So the speed is here in this question, so meters per second, so 7 squared. And again, times in the numbers together. Make sure though that you square the number 7, so don't put 7. 0.5 times 50 times 7. Make sure the number 7 is squared first. Answer you should get 1225. And again, joules has been given for you. So again, if that is not there, make sure you check and make sure that you write the units on. Okay, so the second part of this, of Spec 1, which is the required practical, is specific heat capacity. So we're going to run through what it is, we're going to run through what the practical is, and then we'll do one practice exam question exactly like we've just done. So, specific heat capacity. The definition. So if you're asked what specific heat capacity is, it is the amount of energy required to heat 1 kilogram of a substance by 1 degree C. Okay, so that is the definition. So the equation which you get is the energy transferred so you do mass times the specific heat capacity times the temperature change. So the units degrees C for temperature, kilograms for mass, energy is joules, specific heat capacity is joules per kilogram per degree C. Okay, so the required practical. So for the required practical, the aim of it is to work out the specific heat capacity. Okay, so you might have been given in the practical a metal block, and in that metal block you would have two things. One of them would be the immersion heater, and the other one would be the thermometer. Okay, so you would have your metal block, you would have the thermometer, and you would have your immersion heater. Okay, so how do we use that equipment to work out the specific heat capacity? So I'll run through the method first, and then how we would use our results that we collect in the method to work that out. So the first thing we would have to do is we would have to take the mass of the metal block that we are using. Number two, we place the immersion heater into the block, so there will be a hole in there where you can put the immersion heater. Okay, now the immersion heater would have wires coming out the top of it. Okay, so what you have to do is you have to connect in a series circuit the ammeter, and that's going to be used to measure your current. You would need a power pack, and obviously you would have the heater as well. So all connected in a series circuit. You would also need to add in a voltmeter. Now this is connected across the power pack. Okay, next you pipette a small amount of water pipette a small amount of water into the hole where you put the thermometer, and then you put the thermometer in. And that's obviously to measure your temperature with. So once you set the practical up, you would switch it on. So 12 volts, switch it on. And during this time, you need to record a few things. So you're going to record the potential difference using your voltmeter. And you're going to measure the current using your ammeter. And at the same time, you're going to record the temperature for 10 minutes. Okay, so that's the method. So you have to know how to use the results that you have collected from this method. So I'm just going to grab another piece of paper. So this is our equation for specific heat capacity. So the first thing we need to do is, obviously we have our mass, we measured that during our practical, it was the first step we did. We want to work out the specific heat capacity. So the first thing we need to do is we actually need to calculate power. So we need to use the equation, power is current times potential difference. Okay, so these two things we have just measured in our practical. We measured the current using the ammeter and the potential difference using the voltmeter. So current times potential difference will give us our power. Now what we can do then is we can times our power by 1,000, and basically that will give us how much work has been done. And work done, like I told you earlier on, is the same, or sometimes both referred to as energy transferred. So we've worked out our energy transferred, and then we've worked out our temperature change. So we'd have to rearrange the equation then to put our results in. Normally you will get given results to use, okay? So you wouldn't be expected to go with any results, obviously. So energy would go on top. And then to work it out, the specific heat capacity, you mass times the temperature change. They might even give you a graph to look at, or they might even ask you to draw a graph. So along the bottom, you will put your work done in joules, and up the side would be your temperature. And hopefully you will get a straight line. So that's the required practical for specific heat capacity. So we've got one exam question to show you how they could test you in the exam. So I'm just going to go through this part here. Okay, so this is the calculation for specific heat capacity. So it gives you a little bit of information above. So we're going to look at this part here. So a metal worker quenches a steel rod by heating it to a temperature of 900 degrees C before placing it in cold water. It has a mass of 20 kilograms. The final temperature of the rod is 50 degrees C. Calculate the energy transferred to the steel rod from the steel rod to the water, the specific heat capacity it's giving you in the question. Okay? So go back to our question. Energy transferred, mass times specific heat capacity times temperature change. Now the mass is here, 20 kilograms, times by the specific heat capacity, which is here, 420, times by temperature change. Now please don't just go straight for the highest number. It's a temperature change. So its maximum temperature was 900. It then cooled to 50, okay? So the temperature change is 850 degrees C. So times all the numbers together, and then you can put your answer in, which is as below. Again, check that unit is there, and if it isn't, you do need to add it in. Okay, so that's everything for Spec 1. We're just going to take a short 2-minute break while we just change over to Spec 2, where MCD is going to take over. Mr. McDade, you are up. Over to you. Perspective.
Right, hello everybody. So we're over to Spec 2 and we are going to be looking at the electricity topic this evening for the next 15 minutes or so. So first of all, just starting us off is when you're thinking about electricity, electricity is all about electrical charge, and electrical charge is caused by electrons. And those electrons can move through a circuit, and when you have a flow of electrons, that is your electrical current. So your electrical current can be flowing through a wire, and the time is how long it flows for.
Mr. McDade, you've got some real fans on the chat
Okay,
right now.
now if that is flowing, and we have the time, 1 amp is 1 coulomb of charge flowing for 1 second. So we have a relationship between the charge, the current, and the time. Okay, so if, for example, you had a current of 5 amps and it was flowing for 5 minutes, we can work out that the charge is equal to the current of 5 amps times not 5 minutes but 300 seconds. So that means that would have been a charge of 1500 coulombs. Nice and straightforward, okay? And if you want to take that as a triangle, we've got I, T, and Q. Okay, so just to recap there quickly, charge is caused by electrons and current is a flow of electrons, and you can calculate the charge by multiplying the current by the time to give you your answer in coulombs. Okay, so now that we understand what charge is, we can now move on to looking at a little bit about electrical circuits, and in particular we're going to start off with one of your required practicals. Okay, now one of the required practicals investigates a wire, and we are looking at the resistance in the wire and how we can change the length of the wire. So if we are changing the length, that is our independent variable, and the resistance becomes our dependent variable. Okay, so we have other things that are going to be our control variables, and that will be the potential difference in the circuit, it will be the wire, its thickness. So in the experiment, what you do is you set up a circuit. Your voltmeter is always in parallel in your circuit, and your ammeter is always in series. So in this experiment, you have a very straightforward results table where you have the length centimeters will do for the length. And what you will take readings as you move this crocodile clip here along the wire of the meter ruler. And every time you move the wire, you will measure the potential difference in volts, and you will measure the current in amps. And you need a final column at the end here, because we are going to use this equation, V equals IR, and we are going to work out the resistance of the wire in ohms at that particular length. So you rearrange this equation to give you R equals V divided by I. So this question, so you might have 10, 20, 30, 40, 50, and you would expect to get some numbers that might do something like this, okay? And what you will notice is that as the length of the wire goes up, the resistance goes up, okay? The other factor that affects the resistance of a wire is its thickness as well as its length. So you would end up plotting a graph for this. Your independent variable always goes on the x-axis, which would be your length, and your resistance would go on the y-axis, and you would end up with a straight line because it is proportional. Okay, so there we go. So that explains your first required practical, which is the resistance of a wire. Now, moving on to the next part, we're just going to reinforce and remind you of the equation that V equals IR, okay, or R equals V divided by I. Okay, so if you look in the diagram, we've got a potential difference of 12 volts here. We know the current is 6 amps, and we know the resistance of this resistor on its own is 3.5 ohms. So they're asking you to calculate the total resistance. So the total resistance is the resistance of everything here. Okay, we already know V, we already know I, and they've even given us the formula. So the resistance is equal to the potential difference of 12 volts divided by the current, which is 1.6 amps. So that's volts, that's amps, okay? And you will work out an answer here, okay? I'm not going to work it out for you, you can do it for yourself. And your answer, of course, is in ohms because it is resistance, okay? Just a quick calculation in my head, yeah, 7.5 ohms. I think you'll find is the correct answer for that one. Okay, don't forget, a little bit of tip for you, highlight what you know, okay? They've tried to confuse you here because they've given you one of the resistances here, but you didn't actually need that to answer the question, okay? Just going to move on to a slightly trickier one, okay? Remember, V equals IR, R equals V divided by I. Same again, we've got our potential difference in volts, our current, and a different resistance here. They're asking for the potential difference across just X this time. So what do we know about X? Well, we know that we know R and we know I, so V equals IR. So it's equal to 2 times 3, so the potential difference is 6 volts. Okay, now we've got to do the same. We've got to work out the potential difference across Y. Okay, well, what do we know? Okay, well, what do we know about the whole circuit? All right, it's a series circuit. So in a series circuit, the potential difference in these two resistors, okay, is added together to give you the 18. So we've got 18 total. We've just worked out that the potential difference across X is 6 volts. So 18 minus 6 gives us a potential difference across Y of 12 volts. Okay. Again, they're asking you for the total resistance in the last part of the question. We know that V equals 18. We know that I equals 2. So R equals V divided by I, which is 18 divided by 2. So the total resistance is 9 ohms. Okay. Now then, moving on. Your next required practical. Okay. You might see this referred to as IV characteristics. What does that mean? It basically means whatever component you put in here, we are going to look at what happens to I, the current measured on the ammeter, and V, the potential difference measured here. And we can change the voltage in the circuit with this thing here, which is a variable resistor. It's dead straightforward. You put your component in. That can be a lamp. It could be a fixed resistor. But it could also be a diode. It could be an LDR, a light-dependent resistor, and it could be a thermistor. Okay. And what you will do is you would change the variable resistor, and you would record from the meters the voltage and the current, and you would put them on a graph and see what your outcome was. Okay, dead straightforward, very simple circuit. Remember, your ammeter's in series and your voltmeter is in parallel. Now, here's an example of what you would end up with. Just going to pop that back, because also what you would do is you would go from positive down to negative voltages. All right, so we're looking at how the characteristics happen when you've got both positive and negative. And you would end up with graphs that look like this. Okay, this one here is a straight line. If it's a straight line, that means we have something called an ohmic conductor. So what that means is, right, we have a proportional relationship. So it doesn't matter what the potential difference is and what the current is, the gradient, which is also the resistance, stays the same. All right? And an example of that would just be a normal resistor. Here, this very distinctive S shape is a lamp. Okay? So, what do you notice? The gradient changes. The reason the gradient changes is because the resistance changes. Why does the resistance change? It's because it heats up. All right? So that's why we end up with this very distinctive S shape. Now, what do we have here? Well, what we have here, we only get a current with a positive potential difference. Right? So in other words, this component here only allows the current to flow one way, and that is a diode. Okay? So just a quick reminder, that's a resistor, that's a bulb, and this one here is a diode. Okay? Very important component because they can protect the current going the wrong way around a circuit. Okay? Right, moving on. An exam question. Okay? They're asking you to investigate how the current through a lamp affects its resistance. And they've given you all of the components. All right? So, describe how the student could use her circuit to investigate how the current, how the current affects the resistance. So what's her circuit going to be? You're basically describing the electrical circuit you saw 2 pages ago, right? So we will have a lamp, a ammeter, and variable resistor, all in series. You put the voltmeter in parallel with the lamp. Okay, you change the resistance using the variable resistor. And then you will record V and I at different settings. Finally, you would actually repeat the experiment with the battery reversed. So that means you get your positive and your negative readings. Okay, so look here, change. Right, what are you changing? What are you recording? Your independent variable and your dependent variable every time. Okay, so that there is a little quick question on your second required practical. Right. Moving on to something which you've done all the way through school, all the way from year 7, is looking at different types of circuits. So what do we have here? We have a series circuit. Okay, we've got one continuous loop. Okay, now, if we were to measure the current at different points in this circuit, by 3 different points, the current is the same everywhere. Okay, current's the same in a series circuit. Now what we have here, again, we've got 2 resistors in a series circuit. The components that we are interested in are in series. And what you will notice here is that we have our voltmeters in 3 positions, and V1 is equal to V2 plus, Vs is equal to V1 plus V2. So what that means is that the potential difference is shared between the components. Okay, shared. Okay, nice easy question. They tell you that you don't know what that one is, but they tell you what these 2 are. Okay, really easy for you to work that out. Now comparing a series circuit with a parallel circuit. So if you'd see here, we've got the bulb in the one loop, and then you have a separate loop with your second bulb, all right? And what you have here is you've got a point here where the current can decide which way it wants to go. right? So what happens here, if we put an ammeter there and call it A1 and A2 there, the total current in the circuit, which we'll call AT, is A1 plus A2. So what's happened here is the current splits. Okay. Now then, what have we got here? Same again. We have our first resistor and our second resistor. Now this time, something very important. Okay, the potential difference is the same in each loop. Now this explains a couple of things that are quite easy to understand. So first of all, you might notice that when you've got your Christmas tree lights on and one of the bulbs blows, right, that all of the others stay on. What you will also notice is it doesn't matter how many bulbs blow, all of the others remain the same brightness because the potential difference is the same in each loop. It also explains something else. It explains your lighting at home. So when you turn other lights on in the house, it doesn't affect the brightness of the light in the room you are sitting in. Again, because the potential difference in the circuit is the same in each room, no matter how many lights you turn on. Okay. Now then, one thing you will be asked to calculate is power in a circuit, right? Power is equal to the current times the voltage. Okay. Now, that's dead straightforward. If you take a typical TV, what do we know? Well, let's just say it's 240 volts. All right? And let's just say on the back of it, it tells you that its power is 40 watts. Power is measured in watts. Current is measured in amps. And V, voltage. Right? So, what do we know? We've got our voltage, our power, and we don't know I. So you could be asked on the higher paper, for example, to work out that I is equal to the power of the appliance divided by the voltage, which would be 240 volts divided by 40 watts, which gives you a current of 6 amps. Okay, nice and straightforward. Here we go. Here's your triangle for that. I times V, power. Now you might notice that in your equations that you've had to learn, you have another equation which is P equals I squared times R. Okay, so what's going on there? Well, it's dead straightforward. What they've done is they've taken the V, which we know is equal to IR, and they've replaced the V in that previous equation with IR. Okay, so that basically means P equals I times R. So what that means is you can do similar calculations if you have just the current and the resistance. All right, so you might have a bulb. I'm going to stop calling them bulbs because that's what we put in the ground and they turn into plants. Right, and we have an ammeter. Okay, and the ammeter is reading 2 amps, and the bulb has a resistance of 5 ohms. Right, so the power is equal to 5 squared. No, it's not. 2 squared times 5, which is 20 watts. Okay. Now then, that is the end of Spec 2, the electricity topic, and we are going to take a very quick 2-minute break, guys. Thank you. Go. Do you want them?
Got some much appreciation from the colour. Make sure you moderate any rag.
The sun's gone in now, we can get rid of it.
Thank you, Miss Hughes. Okay, so I know that we are running a little bit over, so I'll try and get through as much of Spec 3 and Spec 4 as I can. So, starting off with density then. So, density is the mass for a given volume. Now, density, you do not get the equation. You don't get given the density equation. So, to work it out, it's mass in kilograms divided by volume in meters cubed. Okay, if you wanted to put that into a triangle, so similar to what we said for you in the chemistry exam about labelling your periodic table, any of these equations that you don't get given, as soon as you're allowed to write, I would pop that on the back of your paper or in some space. So M for mass, remember that has to be in kilograms. A tip is that just check your units, so if they give it you in grams, then obviously remember to convert it. V for volume in meters cubed. And then density, and the unit for density is kilograms per meters cubed. Okay, so then we're going to do a little bit on the 3 states of matter. So hopefully you're all really familiar with this, so I can go through it nice and quickly. So solid, the particles are very close together and they are in a regular pattern. Now they don't move much, they just vibrate. So they're close together. And it'd be a really nice 6 marker to talk about the arrangement and the movement of the particles in the 3 states. They vibrate, but they do not move from place to place. Liquid. A common one when drawing the particles in a liquid, people just do them as a less dense gas. You leave too many spaces. The particles are still really close together. It's just that they're not in a regular pattern anymore. So again, close together, so don't make that mistake of drawing it just as a denser gas. And then these ones, so it's not regular like you just saw in the solid. And these can move around each other. And then the last one would be the gas. So they are far apart, no pattern, and they move rapidly and random. Okay, and they're moving really quickly. Now, in terms of density linking into the 3 states of matter, hopefully it's quite obvious that your solids have your high density. You might even describe it as a very high density. Liquids then being high, not very high. And then gases being low density.
So they would have a low mass for a given volume, whereas solids would have a high mass for a given volume. Now the density required practical, again, it's a nice easy one, but it did come up on last year's exams. So again, the chances of it coming up is unlikely, but it might come up in a different way. So rather than a method, it might ask you an equipment question or so on. Now it changes depending on if you're trying to work out the density of a regular shape or an irregular object. So both of them start off the same way. So if we think about density, remember it's mass divided by volume. Okay, so for both of them, to work out the mass, you're going to use a mass balance. Okay, and just remember that your units have to be in kilograms. So either check the settings on the mass balance or convert if it's given it you in grams, okay? Because remember, if it's given it in grams, you divide it by 1,000. Now the regular one is probably the easier one to measure, so you can actually measure the volume. So the dimensions are easy to measure with a ruler. Okay, and then to work out your volume, if it's a perfect cube, it would just be the length of the side cubed, or it would be the height times the width times the length to calculate your volume. Okay, now with the irregular one, the dimensions you cannot measure with a ruler. So this is where you use an important piece of equipment called a Eureka Cam. Hopefully you've heard of a Eureka Cam. Now with the Eureka Cam, you fill it with water. You place the irregular object in the water. Might have to start running out of room. Okay, and then this will displace some of the water out of the Eureka Cam. Now the water it displaces, the water it pushes out of the Eureka Cam, is equal to the volume. So you need to measure this water with a measuring cylinder to give you your volume. Okay, so two ways of doing it depending if you've got a regular. Remember, a regular shape is one where you can measure the dimensions with a ruler. Irregular, you can't. So that's where you have to use your Eureka Cam. If we quickly look at an exam question then. So two large semi-precious stones are dissolved. A student has to find out the material that each of the two stones is made of. The student does this by determining the density and they want to measure the volume of stone A. Stone A cannot be measured using a metre rule, so therefore you know it's an irregular shape, so you would use a Eureka Cam. Okay, it would displace the water. You'd measure this water using a measuring cylinder and put this into your density equation. Okay, hopefully nice and easy. Okay, on to some more exam questions. So which piece of equipment could the student use to get a more accurate measurement on the length of the stone? So obviously they've used a metre ruler and it's the vernier calipers that would give you the more accurate measurement on the length of the piece of stone. Use the following equation to calculate the volume, so it's actually literally giving it you, so it's just times in all those three numbers together. To give you an answer of 11.2. And then you can see here, It gives you the mass in grams, so hopefully that should be a red flag because we know that the units need to be in kilograms. So we need to divide it by 1,000, so the mass becomes 0.056 kg. Calculate the density of the stone. Oh, actually it says in grams per centimetres cubed, so we can leave it the same. So it's your mass is 56, divided by your volume, which you've got from there, which is 11.2, to give you an answer of 5. So that's an important one there to check your units. So if it wanted it in kilograms per centimetres cubed, then we'd have to convert. Normally it does want it in kilograms, so just watch out for that because that's a little sneaky one. Okay, changes of state then. How are we doing for time, Mr. McDade?
Well, we're fine.
Okay, so changes of state then. Hopefully again you know that your three, we've got solid, liquid, gas, and again this shouldn't be anything amazing. So solid to a liquid is called melting. Liquid to gas is boiling. We're going to talk about what evaporation is after. Gas to liquid is condensation. And liquid to solid is freezing. Okay, now in terms of exam questions, which we're going to look at in a second, there's a few things that we need to know about these. So all of these are physical changes. So that means that nothing new is made. They're not chemical changes, they're physical changes. Now, when you are heating a solid, so going from a solid to a liquid, you are increasing the internal energy, okay, until it melts. And then when you're going from a liquid to a gas, you're increasing the internal energy, which is then boiling. And then when you're going the other way, you are reducing the internal energy. So gas to liquid, you're reducing it, condensation, liquid to solid, reducing the internal energy. Now, in each of these, so each of these changes of state, mass is conserved. Okay, so because you're literally, it's just a physical change from one state to another. There is another change of state where it goes straight from a solid to a gas. So carbon dioxide is a substance that undergoes this change of state, and it's called sublimation. It's called sublimation back as well, so gas to solid. Sometimes you might see it called desublimation, but you're pretty safe calling it sublimation. Now, in terms of some key definitions before we sort of go on to the heating and cooling curve. So internal energy. So it could ask you what this is. So internal energy is the energy stored in a system by the particles. Now, internal energy is made up of two things. So the internal energy is the kinetic energy plus of the particles plus the potential energy. Sorry, this table must be on a slant. Internal energy is the kinetic energy plus the potential energy of all the particles. Okay, so the internal energy is the energy stored in a system by the particles, and then to work out your internal energy, it's the kinetic plus the potential. So one question that we'll see in a minute is a liquid would have a greater potential energy because more energy for the change of state is needed to break the bonds or to break the forces. So if we look at this question, the particle model can be used to explain the particles, the properties of gases, describe the direction of the motion of the particles of gases. Hopefully you've got that it's random. You could also have in all directions or random motion. This is an interesting one. So explain why heating a gas increases the average speed of the gas particles. So explain why heating increases the average speed. So hopefully you would say that heating increases the temperature. Temperature is proportional to kinetic energy. So what that means is that as you increase the temperature, you're going to increase the kinetic energy, and if the kinetic energy increases, then the speed increases. Okay, again an interesting one here. So water can exist as either a liquid or a gas at 100 degrees C. Explain why a mass of gaseous water at 100 degrees C contains more energy than an equal mass of water at 100 degrees C. So this is where, so we've got a gas and a liquid. So this is where you go back to your changes of state. So the gas has undergone one more change of state. So you need more energy to turn it into a gas. So what it's looking for is energy is needed to change the state of the water. To break the bonds. Okay. Then we've got the heating curve. Okay, so remember it can be the heating or the cooling curve. I'm going to look at the heating curve, and then obviously it's just it can be the other way round. So when the line is going up, so here the temperature is increasing. So you can also see here it's going up, so the temperature is also increasing. And we've got the temperature increasing here. Now you'll see that you've got parts of the graph where it's horizontal. That is where your changes of state are happening. So you can see that the energy here, it's not being used to change the temperature, it's actually being used to break the forces or to break the bonds or even weaken them depending on what type of molecule you've got here. So if you're starting off as a solid, you're going to heat it, and then the change of state that would be happening here is melting. And all you would have to do is read off, I ain't got a ruler, but obviously you would, and this point here would be the melting point. Same here, so then it's melted, so you've either weakened, using the energy to weaken the forces, and then you continue heating it. So once that change of state has occurred, then the energy will then be increasing the temperature until you get to the next change of state. So if we're melting it here, then here it would be boiling. So again, going from a liquid to a gas, and you would read off here, and this temperature would be your boiling point. Now, when you're increasing the temperature, you're increasing the kinetic energy, and when you're changing the state, you are increasing the potential energy. Now, again, it could be the other way round, so starting off as a gas, going back to a solid, it would be the same thing, but obviously it would be the other changes of state, so condensation, and then followed by freezing. Now, we mentioned evaporation, so evaporation is different to boiling. So evaporation is when the surface, so there's only enough energy for the surface of the liquid to turn into a gas. The actual change of state from liquid to gas is called boiling, okay? On to an exam question on the heating curve. So it says here, it wants you to explain what is happening to the substances between sections A and B and C of the graph. So we can see that A and B, it's horizontal, so we know it's a change of state that is happening. So the actual change of state would be melting, going from a solid to a liquid. And then the second mark for the A and B section is saying what happens to the temperature. So because it's a change of state, the temperature is constant. And then between B and C, okay, the temperature, so it's not horizontal this time, the temperature is rising until it reaches, and remember we said this line across here is the boiling point. So 2 marks if we're saying that the temperature is increasing or rising until it reaches its boiling point. Okay. Internal energy then. So we've got again a few more definitions here. I think I've done a lot on internal energy, so I think actually we can go on to specific latent heat. So again, we've got a few definitions. So latent heat, and I'm just going to go through these, and these are ones that you would be expected to know. Latent heat is the energy needed to change state. Then we've got something which is specific latent heat. I'm just going to shorten it so it doesn't take me too long to write the definition out. And that is the amount of energy required to change the state of 1 kilogram of the substance with no change in temperature. And that breaks down into the specific latent heat of fusion and the specific latent heat of vaporization. So specific latent heat of fusion. So again, very similar definitions, only the odd bit that is changing. So it's the energy required to change 1 kilogram of a substance from a solid to a liquid. Okay, so I'm just going to put solid to liquid. I'm not going to write the whole thing out. So it's 1 kilogram of a substance from a solid to liquid with no temperature change. And then specific latent heat of vaporization. I think I've gone off actually. There. Again, I'm not going to write the full thing out. Better? Yeah. Again, so it's 1 kilogram of a substance from liquid to a vapor with no temperature change. Okay, so important that you learn the difference about those. Now, there is actually a formula for specific latent heat, and you do get given it, but you don't obviously get given it in the triangle. So it's E equals M times L. E is the energy for a change of state in joules. M is the mass in kilograms, and L is specific latent heat in joules per kilogram. Okay, so if we were to put that into a triangle then, it'd be E at the top and then M, L on the bottom. Remember, this line is a times and this is a divide line, okay? Now, I don't think we're going to have time to go through this one. Now, I do want to go through this one because, again, this was a big tip from your physics teachers, that if a calculation is worth 5 marks, then you need to be using 2 triangles together. So this is an interesting one that we'll just quickly do together before we go on to atomic structure and radioactivity. So water vapour is a gas. Gas changes state when they cool. The figure below shows the condensation on a cold bathroom mirror. The volume of 2.5 times 10 to the minus 5 metres cubed of condensation forms on the mirror. Water has a density of 1,000 kilograms per metre. The specific latent heat is this, calculate the energy released. So if we were just to go straight to the energy released, it's mass times specific latent heat. We're not given the mass though, but we are given the volume and the density. So what we need to do first is use the density triangle. So if we think back to our density sheet, if I can find it, probably on the floor. Okay, so remember density on the bottom, mass, hopefully you remembered that mass had to be in kilograms, and then you've got your volume and you've got your density there. So the first thing you would need to do to work out your mass is you would do your 2.5, which is your volume, times 10 to the minus 5, times by the density, which is 1,000. Okay. To give you an answer of 0.025. This then becomes your mass in kilograms. Okay, and now you've got your mass, you can use your second triangle. So to work out energy released, it's your mass in kilograms, which you've just worked out at 0.025, times the specific latent heat, which it gives you here, 2.26 times 10 to the 6 joules per kilogram. And that gives you out an answer of 56,500 joules. So again, if you're looking at a calculation for 5 marks, you need to be putting 2 triangles together. Okay, that's a really, really common theme. Okay, 2 more to do. Atomic structure, shall we just go straight to radiation because we've had that in chemistry? Yeah. Okay, so nuclear radiation, this again was a big one from your physics teachers that they think is going to come up. So you've got the 3 types. You've got alpha, which is a helium nucleus. Okay, and remember in a helium nucleus you've got 2 protons, 2 neutrons. Beta is a high-speed electron. You can't just say an electron, okay? You have to say a high-speed electron that's been ejected or emitted from the nucleus. And then gamma is a wave. Okay, now if we look at masses and charges, the alpha the alpha radiation is the heaviest. Okay, with the greatest mass, and it's got a positive, well, it's got a 2 positive charge because of your 2 protons. Beta is very small, it's only an electron. And it's got a negative charge. Again, hopefully this is some crossover from your chemistry. And then gamma, because it's a wave, no mass, no charge. Okay, it does mention on the spec that you can have neutron radiation as well. There's not too much more you need to know about that, but it can be a form of radiation. So if we look in detail of the 3, because what's important about these is you need to know about them so you can actually apply them to the question, because it's very commonly an application question. So alpha, we've said obviously it's the heaviest, it's got the highest charge, and it's the most ionising. Because it's the most ionising, it's most likely to be stopped. Therefore, it will only travel short distances before it is stopped and ionised. Okay, it can be stopped by something as thin as paper. Okay, so it's the most ionising, most likely to be stopped, only travels short distance. We're talking a few centimetres. Beta. Okay, so beta is smaller. It's got a lower charge. It's less ionising. Now, because it's less ionising, it will travel further, so we're talking several metres. and therefore it's harder to stop. Okay, and it's usually stopped by something dense like aluminium. Aluminium. Okay, so we're talking paper would stop alpha, but you need something a bit denser, you need aluminium to stop beta. Gamma then is only stopped by a lot of lead. Okay, so it's got no charge, no mass, only stopped by a lot of lead. Okay, nuclear equations then, and I know but we're already over, so I will quickly go through this. So alpha, what colour shall we use? You lose a helium nucleus. Remember, which can be represented as 2 and 4. The bottom number being the atomic number, the number of protons. The top number is the mass number, which is the protons plus the neutrons. So if I give you an example of an alpha radiation or nuclear equation, sorry. So you've got radon, which 21986 would then change to polonium at 215 and 84. So with alpha, the bottom number goes down by 2, the top number goes down by 4, so plus your helium nucleus. So alpha, both numbers are changing, okay? When we look at beta in a second, it's only the bottom number that changes. So if both numbers are changing, then you're looking at alpha, and you can see the bottom number goes down by 2, the top number goes down by 4, and that's because you are losing a helium nucleus, okay? Just a bit distracting back in the headquarters. Mr. McDade's left his station. Beta is where, I'll show you an example first to make it easier. So we've got carbon, 14 and 6, turns to nitrogen, 14 and 7, plus an electron. So what happens, how to recognise if it's beta? The atomic number goes up by 1, but the mass number stays the same. So what happens is a neutron from the nucleus turns into a proton, so that's why the atomic number goes up by 1, and emits an electron. Remember, a beta is when you've got a high-speed electron emitted from the nucleus. So nice easy way to work it out. If both numbers are changing, you've got alpha. If it's just the bottom number that's changing, you've got beta. Okay? Now, I think that's probably all we've got time for. Now, the separates video, we will be popping on any second now. Mr. Clee actually pre-recorded this today for you because he can't be here with us tonight. So we'll just upload it, and he spent his own time recording that for you today. So that will be up within the next 5 minutes. Thank you very much for listening. Good luck. Remember, your booster is period 4 tomorrow. Please rewatch this video if you need to. Thank you. What the hell were you laughing at? Do you know how paranoid that makes you? Tell me.
How do we calculate the acceleration of McDade's toes?
What the hell?
Right.
Tell me more.
You can either end the event, archive it on YouTube, or keep it active. You can resume it later. We're going to finish the event, aren't we? Yeah?
So, this John Cena said...
Yeah? Oh God, go on. Is it bad?
McDade said he was, he said.
Something about McDade should come dressed as a unicorn
Gone to the prom.
So then he commented saying, have you got any particular colour in mind?
Oh my God.
And then he put, I think white with pink hoops would suit him.
Who is this John Cena?
I don't know. Right, end YouTube live session. You can either end the archive it on YouTube or keep it active. No, we're going to finish the event.